Well, first of all, I'd like to say thank you very much for inviting me to speak this afternoon, and I'm only sorry the occasion for my opportunity is such a sad one. We can all remember Peter, and I tend to look forward to his book enormously. Thank you. I think Peter's planned talk this afternoon would have challenged one of the basic tenets of 20th century physics, and that is that the geographical location of an axis of spin cannot change without exerting massive forces. Peter's point was that yes, it could, and so the Earth could have rotated. It's a fascinating view on how physics could have got it wrong. I'd like to start on the same general theme and challenge one of the foundations of 20th century physics, which assumes that the speed of light of space in space is constant. And we'll see that it isn't. We'll also find that the speed of light on Earth can be different in different directions, and that's to say it's anisotropic. But first I'd like to take you back to the 19th century and the debate about the nature of light, when there were two main theories at the time, and both had to deal with the problem of how light crossed the assumed vacuum of space. The ballistic theory, following Newton's corpuscular theory, thought that light consisted of small particles, and they could cross the vacuum like bullets, so there was no conceptual problem there at all. The other theory thought that light was a wave, but scientists knew that light couldn't cross a vacuum because all waves need some form of medium in which to travel. Something needs to vibrate in order to let the wave pass. So the scientists of the 19th century suggested that space was filled with a substance which they called ether. It was simply invented to provide a medium for light to travel as a wave. Now Bradley in 1728 had discovered stellar aberration, which means you have to point the telescope forward in the direction the Earth is travelling through space in order to, as it were, catch the light falling into the telescope. The analogy being with pointing an umbrella forward when you're walking forward into vertical rain, you have to point your umbrella forward to keep dry. So aberration could be explained by both the ballistic, the little bullet theories, and also by the wave theory. But the ballistic theory was easier to understand and was more popular for a time. And that was until 1861, when Maxwell, his development of the equation of electromagnetism, proved that light was itself an electromagnetic wave, after which the ballistic theory fell out of fashion. But once Maxwell had proved that light was an electromagnetic wave, that proved effectively, for scientists at the time, that space must be filled with an ether. So then, of course, the race was on to find it. So, in terms of the transmission of light, why does Maxwell's equation show that light has to be an electromagnetic wave? Well, first of all, don't worry about too much about the maths, but the equation on the top left here is a wave equation developed directly from the Maxwell equations, and the speed of wave is given by these two quantities here, mu and epsilon, which on the right here are related to the speed of light c through that equation there. It basically means the speed of light travels as a wave depending on those two quantities, mu and e, which are electrical and magnetic parameters of the medium. Okay, it's important to remember that. The speed of light is defined as derived directly and only from two electrical and magnetic properties. Now the bottom diagram shows how light actually travels. You've got an electric wave in red vibrating in one plane. You have a magnetic wave in green vibrating in a plane of right angles, and the energy of the wave is propagated in the third direction, shown by the black arrow, and the energy can be defined by the pointing vector, which defines the fact that the energy is transmitted at right angles to both the electric and magnetic waves. So that's basically what Maxwell found, and that proved that the electromagnetic wave of light was itself an electromagnetic wave. Okay, so according to Maxwell, epsilon and mu, these quantities here which define the speed of light, according to Maxwell, they were constants in the ether of free space. And that meant that c, the speed of light, was also constant and isotropic. That's to say it had to be the same in all directions. But the ether that had been invented to let light pass through the vacuum of space, it had to be very strange stuff. First of all, it had to be stiffer than steel to allow the light waves to vibrate in it at the frequency they do vibrate. And yet it had to be tenuous enough to allow the planets to pass through it without getting stopped. So it was very important stuff. So clearly the scientists of the time wanted to try and find it. Now, the ether model was developed based on Bradley's aberration, which proves that if there was an ether in space, and Earth here is travelling in space around the Sun, the ether was not being dragged along with the Earth like the atmosphere, because if the ether was being dragged along like the Earth's atmosphere, you wouldn't see any aberration. So the ether had to be stationary in space, which is what Fresnel proposed and what everybody believed. But that means if the ether was stationary, then the Earth would be flying through it with a headwind velocity, would be going through it with a velocity of 30 kilometers a second, which, like running into a stationary air but generating a wind by running against it, looks as though you've got an ether headwind of 30 kilometers a second backwards. Okay, so that's what people went looking for. Now the Michelson-Morley experiment, and here is the diagram from their actual paper, is a very simple experiment in principle. They basically used a source of light over here, split it through half-silvered mirrors, so the part of it went this way and part of it went that way, and then recombined on reflection of the end mirrors into the telescope here, and it generated an interference pattern. So the principle of all Michelson-Morley experiments is you use one beam of light, you split it into halves, you send those two on halves of right angles, recombine them, and look for the interference. So quite simple. So that, according to Michelson-Morley calculations, would show the headwind. Now, the way it would do that, of course, is because if this path is running into and with a headwind, you get a different velocity of light, net velocity, compared to the cross-linked path. In exactly the same way as if you're swimming into up and down the river, you go at a different speed compared to the bank on average than you do if you try and swim across and back the river. So the point is that Michelson-Morley didn't find the 30 kilometers a second headwind. What they reported was that the relative velocity of the Earth and the ether was probably less than 1/6 of the Earth's orbital velocity. And that completely undermined Fresnel's theory of aberration in a stationary ether. So they should have found the headwind. But because the expected headwind of 30 kilometers a second had not been found, just it was less than 1/6 of what they were looking for, is what they did find. Because they couldn't find it all, the scientists concluded that the stationary ether didn't exist at all, and therefore that the smaller effects, the 1/6 or 5 kilometers a second that Michelson-Morley did find, must have been experimental errors. Okay? But it was still necessary to explain the aberration. Because if you don't have the headwind, you can't have the aberration. And that led Fitzgerald and then Lorentz to propose that all things contracted in the direction of their motion, and that led on to Einstein formulating his special theory of relativity on the basis that the ether couldn't be detected. Now, how did the Lorentz and Fitzgerald contraction work? Well, we're talking about average speeds in different lengths. And basically what Lorentz and Fitzgerald both proposed independently was that the leg pointing into and with the headwind in the direction of motion, that had to shrink a little bit. So it actually got shorter, and that explains why Michelson-Morley couldn't find the 30 meters a second headwind. Okay? But then how did that in turn lead on to the development of the special theory of relativity? Well, this is what Einstein was working on, essentially. It comes down to a simple vector addition diagram. If you look on the bottom left here, you've got c is the actual speed of light, and in conventional classic physics, you can have any observer's velocity up here, and you get the measured value of light here. But the problem was that Michelson-Morley demonstrated that you apparently couldn't detect any v here. And yet the principle of relativity said that every observer, wherever they're carrying out their experiments, ought to be able to find the real speed of light here. So what Einstein effectively did was say, well, okay, we measure this, but we'll call it this anyway. Well, forget about this, we can't find it, never mind about it. We'll just say that this is always the same relative to the observer. So, it's a bit of sleight of hand, isn't it, really? You say, well, we'll just call this one because we don't know what this one is. Anyway, if you do that, do the maths, plug that into the equations, what you end up with is four-dimensional curved space-time, and we all know the rest of it. That's special relativity. But that's essentially what he was doing. He was basically measuring this and calling it that. Now, the reason it depends entirely on the fact that you can't measure this velocity according to the Michelson-Morley experiment. They didn't find 30 kilometers a second headwind. So if you can't measure your own velocity, then you can't get from this to this. Therefore, we just say we measure that in the first place. But if you can measure your own velocity, then obviously you can go back to this diagram here. So why couldn't you measure your own velocity? Well, this is because there is a vacuum in space. Remember, you were thinking back in the 1800s, 1905, Einstein's relativity came along. They were still firmly convinced that space was a vacuum. Apart from this strange stuff, ether, which Michelson and Morley couldn't detect. Therefore, Einstein, in the terms of his time, seemed to be on reasonable ground to make one of the postulates of special relativity the fact that you couldn't detect the ether. Therefore, effectively, there was a true vacuum in space. You've got no means of measuring who's moving and who isn't, because there's no ground length, as it were, to measure against. So that's where relativity comes from. Now, the problem with relativity, it turns classical physics on its head. For example, Einstein's special theory of relativity contradicts Newton's third law of motion, that action and reaction are equal and opposite. Under Einstein's theory, Newton's third law can't be true for one moving and one stationary mass, or one moving and one stationary charge. Also, by assuming that c is constant with respect to the observer, this makes Maxwell's equations themselves vary in different frames of reference. You then need to apply the Lorentz transformation to correct for the variance. So it all gets insanely complicated in 4D tensor maths in Minkowski spacetime. But of course we now know, since the 50s, that space is not a true vacuum. It's not filled with an ether, but spacecraft have found that space is full of plasma, and it's full of electromagnetic fields. So there is something there to wave after all. And we can detect it. So we should be able to measure the observer's velocity after all. And shouldn't this fact alone have made scientists reconsider the very foundations of the special theory of relativity? But it didn't. We all know the history of the success of Einstein's theory. Now, less well known is that in 1987, Peter Beckmann derived all the results of the special theory of relativity mathematically, directly from the Maxwell equations and the Lorentz force law, not contraction. And Beckmann just used classical maths without needing the Lorentz transformation or the special theory of relativity at all. So in other words, all those results of the properties as triumphs of special relativity, Beckmann could derive exactly the same predictions from his theory. And what did he do? He made one very simple adjustment to Einstein's theory. He assumed that the speed of light was constant with respect to the locally dominant field, not with respect to the observer. The observer, in Beckmann's words, is therefore condemned to observing without interfering. It's like that. Suddenly everything becomes clear. If you're all velocities with relation to the local field, then you can measure V after all. And you can measure C from your experiments, and therefore every observer can measure this, and they can work out the same speed of light. So we're back to where classical physics said it should be. The principle of relativity still stands. Not the theory of relativity, but the principle of relativity. And so we're back to classical maths. So Maxwell's equations, the interesting bit now is that Maxwell's equations are then automatically invariant under translation. And Newton's third law still applies. Space stays three-dimensional, and time flows on uniformly, as the classical physicists expected. All that simply by assuming that light has a definite speed relative to the medium in which it's travelling, like every other type of wave. And the medium, in the Beckmann model, is the local field. Now, I've briefly mentioned that all experiments purporting to support Einstein's theory also support the Beckmann model, but without needing the contortions of Minkowski tensor maths curved space-time to do it. I'll repeat that. There is no experimental evidence that contradicts the Beckmann model. So, the model is very powerful, and it achieves everything that relativity does, and more, but without causing the problems that Einstein's theory does. And so I've got enormous respect for the Beckmann model, and I'm basing my paper on it today. Now there are a couple of peripheral assumptions in the model, one of which somebody asked me about at lunchtime, that I suggest should be reconsidered in the plasma universe perspective. And the first is that Beckmann related the field to the gravitational field of the Earth because he assumed that the Earth was uncharged. Therefore, the only field Beckmann had available to him, ignoring the magnetic field, was the gravitational field. And he based his argument on the gravitational field. If, on the other hand, the Earth and other bodies in space are charged, as proponents of the plasma universe argue, then the locally dominant field for Earth-bound experiments would obviously be the Earth's electromagnetic field instead of the gravitational field. And bearing in mind that light is an electromagnetic wave, it seems to make more intuitive sense anyway. Now, how does that affect the Beckmann model? Well, it doesn't, because the math is exactly the same whether you talk about the gravitational field or the electromagnetic field. Because neither rotate with the Earth's daily rotation, but both will orbit around the Sun with the Earth. So the mass is exactly the same if you change from the gravitational to the electromagnetic field. So the Beckmann model fits very well with the plasma universe model and a charged Earth. But this is where it gets more interesting. Beckmann's second assumption was that Michelson-Morley experiments gave a null result. They actually disagreed. And I'm not the only person to disagree. This slide here shows the actual results that Michelson and Morley reported, which have taken the numbers from their paper and simply plotted them using Excel. Michelson and Morley themselves reported a result of probably less than 1/6 of the expected headwind. But Professor Higgs later pointed out that Michelson and Morley had made a mistake by taking the average of different sessions with different settings. And that averaged out the effect they were looking for. And you can see that in these graphs here. They did 2 sets of readings on 3 different days each. One set at noon, one set in the evening. The blue lines represent the daily readings at noon or in the evening. The red line represents their reported conclusion. Now you can see straight away that the red line is much flatter and therefore shows much less variation. What is slightly less obvious, but you can see perhaps more clearly on the lower line, is that if you smooth out this darker blue curve, you've got a sine curve starting with the dip and then rising. If you take the other curve, you're tending to get something more like a sine curve the other way around. Now, this is oversimplifying talking about a sine curve model. But what I'd like you to think of is if you've got a sine curve which, if you're trying to add plus sign to minus sign, the answer is 0, isn't it? And that's effectively, disguised a little bit by the random experimental errors, but it's effectively what Michelson and Morley were doing by taking the averages before reporting their red line results. Now, we're averaging out experiments which had positive and negative signs involved, so they were tending to cancel out their results. And they're obviously only averaging over 3 different sets here. If they'd averaged over 30, they probably would have reported an absolutely null result. But the point is they were pretty well averaging out the result they were looking for. Now, when Higgs reanalyzed the blue lines individually before averaging the results the blue lines showed, he came up with an answer that Michelson and Morley had actually found a headwind of about 8.8 kilometers a second. Now, that's still not the 30 they thought they were looking for, but it's a lot further from 0 than sort of 5 they thought they might have found. So neither the original Michelson-Morley experiments, nor in fact all the vast majority of subsequent Michelson-Morley type experiments came up with a true null result. They simply failed to find the expected ether headwinds at 40 kilometers a second. Any non-null results of a smaller magnitude than the ones expected were written off as experimental errors because after 1905 and Einstein's relativity, everyone knew what the answer should be. So if you didn't get a null result, you must have made a mistake. Simple. So, now, I mentioned briefly there the subsequent Michelson-Morley type experiments. That experiment has been carried out by various people over the years in a very similar way. And here's a summary table of their results. Under closer scrutiny, despite what these people reported, none of the results was accurately reported except for those of Dayton Miller. Everyone else had distorted their own data or simply dismissed any larger results as impossible. So very briefly, here's the original Michelson-Morley. They reported 1/6, which was close to 5 kilometers a second. Higgs showed that it actually measured 8.8. Dayton Miller did 3 sets of experiments over the years and accurately reported a series of values round about 8, plus or minus 8, 9. He found something consistently. Illingworth reported less than 1 kilometer a second, but actually the data in his own paper if you analyse it properly, gives something between 2.5 and 6.7. Michelson, Pearson reported less than 1/50th of the velocity they were looking for, but by the time they carried out their experiment, they weren't just looking for the Earth's superheadroom, they were looking for the Sun's orbital velocity around the galactic centre, that was 300 kilometres a second. So their 1/50th, by a bit of sleight of hand, they disguised the fact that the Sun is very small, actually that equates to 6 kilometres a second. They didn't like to say 6 kilometres a second because they didn't want to report 6 kilometres a second, so they just reported 1/50. You've got to look elsewhere, and I think they'll find the 300s. Juice was extraordinary. He carried out a brilliant, well, actually a strange experiment, but a very modern experiment with lasers and all the rest of it. And he reported 1.5 kilometres a second, but actually he states that he projected all our values anyway. Jacega was the most extraordinary experiment. It was a sort of suspended animation type experiment, very, very odd indeed. But anyway, he reported confidently that he found less than 1 kilometre a second. But if you actually look at his results, you could get anything up to 12.8 out of the graphs he presented in his report. He simply doesn't explain the rest of it at all. Anything else is just put down to experimental error. A vague hand-waving axis might have been off-centre. It's just completely unexplained, and he somehow manages to derive the fact that his results are accurate to 1 kilometre a second. So what we see consistently is people reporting what they wanted to see, apart from Leighton Miller, but actually finding something fairly consistently, which was never the 30 kilometres a second, certainly not the 300, but it wasn't zero either. It's quite important. So where does that leave us? If we assume that all the Michelson-Morley type experiments actually found something, what was it and how does that fit with the Beckmann model, which started from the assumption that Michelson-Morley results were truly null? Well, let's suppose that the non-null results were real and actually due to an electromagnetic effect, rather than a small amount of motion relative to a stationary ether. Remembering, of course, that light is an electromagnetic wave. So let's think in electromagnetic terms. So the question then is it possible that the effect is an electromagnetic one? Well, that would mean the speed of light could be anisotropic, that is different in different directions. And I answer yes, of course it is possible. Because first of all, we've seen the speed of light equation already. We know the speed of light depends only on, here's these figures again, epsilon and mu. Epsilon is the electric permittivity, and mu is the magnetic permeability. And they are properties of the medium. And that medium, we now know, is the plasma out in space, called electromagnetic fields. Now, the Maxwell equations assume that these are constant values in the theoretical vacuum of free space. But we've seen that space isn't a vacuum. Okay? So, like anything else, space being filled with plasma and electromagnetic fields, they have values of permittivity and permeability which depend on the plasma itself and the fields. And it's just like different optical glasses which have different refractive indices because the speed of light in each type is different. And again, that comes down to variable epsilon and mu. So the electromagnetic environment, which is dependent on the values of epsilon and mu, must affect the speed of light. And in fact, we know this does happen because you can look at the Stark effect or the Zeeman effect, and they clearly demonstrate that light is affected by the electric and magnetic fields through which it travels. You could also look at the Kerr effect, Pockels effect, Faraday effect, Voigt effect, and the Pockels-Mouton effect, all of which involve variable permittivity or permeability in relation to direction of polarization. So we know that these values change the speed of light. So the non-null results may well be due to an electromagnetic effect. And in the modified Beckmann model, light travels with respect to the local electromagnetic field. So the values of field can change, light's travelling in relation to the field in the modified Beckmann model, therefore it seems as though space is just another transparent medium in which epsilon and mu can vary from region to region. And so the speed of light is not constant in space after all. Okay? Similarly, if the values of permittivity and permeability are affected by the strength and the direction of the electric or magnetic fields in the atmosphere, as they are known to be in space from the Stark effect and Zeeman effect, then the speed of light in lab experiments on Earth is unlikely to be the same in different directions. In other words, it will be anisotropic. Okay? So at the moment, this is just a theoretical construct that it could be different. We don't need to assume that the speed of light is constant. We've got a lot of evidence that in fact it isn't, so we ought to start going back to this equation and thinking, right, unless we can't predict the speed of light unless we know these values. And we know from plasma experiments that they vary, and we know from receipt of astronomical light in the Stark-Zeeman effect that it varies depending on the electric and the magnetic field. So we've got evidence that it varies already. But there's more. In 1851, Fizeau had found that the speed of light is affected by fast-moving water, as predicted by Fresnel's partial ether drag theory. But Beckmann showed that Maxwell's equations predict that the speed of light varies in any moving medium because of changes to the electromagnetic field inside that moving medium. Now, here's a little diagram to explain what that means. Supposing that we've got a moving glass block in a lab experiment. I've chosen to show the electric field E here, going up the page, the magnetic field I've chosen to show here going into the page, and that means the pointing vector, remember that one, which way is the energy going, it's being delivered that way. Now that's in a glass block which is moving to the right this way. Now that all comes from Beckmann's analysis. I mean, I happen to have chosen random, so right angles, but otherwise at random, to demonstrate the fact that in this particular case, the pointing vector is opposed to the velocity vector. And what we find is that the pointing vector of the external electromagnetic fields, if they were in this direction, would actually slow up the velocity of light in this direction. So remember that the velocity of light has effectively got its own pointing vector. Now, if those two pointing vectors, the pointing vector of the externally applied electromagnetic field is opposed to the pointing vector of the direction we're trying to send light in, which is through moving water in the same direction the moving glass block is going, then you'll find that light is slowed down. So it's as though the two pointing vectors started to oppose each other. And it's not simple vector addition, but the principle is that the pointing vectors oppose each other, therefore light is slowed down. And that's what Beckmann showed, again, through the mathematical analysis simply based on the Maxwell equation. It all comes from classical maths from Maxwell's equations. But the interesting thing is how that relates to the Earth and experiments carried out to look for the ether headwind. We saw before, in the previous talk, that the Earth has a magnetosphere. And here's the Earth, this little ball in the middle, and the magnetosphere surrounds the Earth like a bubble. It's a teardrop. A teardrop-shaped bubble, but basically the magnetosphere is a bubble around the Earth that obviously orbits around with the Earth. Now, what does that magnetosphere look like from the perspective of the Sun's electromagnetic field? It looks like a moving medium. So we're back to our glass block analogy, aren't we? If the magnetosphere takes the place of the glass block, and if we add in the known electric field from the Sun, as argued by the universe repelling, and the magnetic field of the Earth, which is correctly shown in this direction, then the pointing vector from the charged Sun and the charged Earth is opposite to the motion of the Earth in its orbit around the Sun. In other words, it looks just like an ether headwind, but not with the same magnitude. Okay? So, in other words, the electromagnetic effect behaves like the expected ether headwind as far as light on Earth is concerned. And the only difference is that it's smaller than the effectively expected ether headwind. So I suggest that at least part of the 8 or 9 kilometers a second actual results that all the Michelson-Morley type experiments actually found may be due to this electromagnetic effect. But the most experimenters weren't looking for it, and so they dismissed it as experimental error. And now, if that is correct, then we already have evidence that the speed of light on Earth is genuinely anisotropic due to electromagnetic field effects, derivable directly from Maxwell's equation. Okay, so just to summarize, the discovery that space is filled with plasma and electromagnetic fields means that there is no undetectable ether in space for light travelling, and therefore Einstein's special relativity is founded on a false premise. Beckmann's model, where the speed of light is measured with respect to the local field, explains all the results of special relativity, but without any of the problems. Beckmann's model fits with the plasma universe perspective of a charged Earth and Sun. The speed of light in space is not a constant. It depends on the variable electrical permittivity and magnetic permeability of the medium. And the speed of light is anisotropic in moving media, and the Earth's magnetosphere is a moving medium with respect to the quantum environment. So, the non-null results of all the Michelson-Morley experiments may contain evidence of this anisotropic. I'm not saying it's necessarily 8 to 9 kilometers a second, but I think that could contain and disguise the real anisotropy, and I suspect we have the evidence for it. So this has been a very short introduction to the subject. I wrote a fuller paper for the Natural Philosophy Alliance earlier in the year, and that paper gives much more details, and this is available online via the NPA for anybody who'd like to read up the details behind that. So thank you all for listening.
Thank you.